Here's a parallelogram on a coordinate grid with vertices at the origin 3, 1, 1, 4, and 4, 5. What's the area? The classical approach says compute the base length, that's the square root of 3 squared plus 1 squared, which gives the square root of 10. Then find the perpendicular height, another square root, maybe some trigonometry. The numbers pile up fast. Or we could compute 3 times 4 minus 1 times 1. That's 12 minus 1, which equals 11. Done. The area is 11. That single calculation is a determinant. Today we'll see why it works. Why a simple algebraic formula secretly measures geometric volume. So why does this work? Let's build the idea from scratch. Take a 2 by 2 matrix. Its 2 rows are vectors. Place them as arrows from the origin. The first row, vector v1, gives one edge. The second row, vector v2, gives another edge. Now connect the tips to complete a parallelogram. Here is the key claim. The absolute value of the determinant equals the area of that parallelogram. This idea extends beautifully to 3 dimensions. Take a 3 by 3 matrix. Its 3 rows become 3 arrows from the origin, 3 edges of a shape called a parallelepiped. A parallelepiped is the higher dimensional cousin of a parallelogram. It's a box whose faces are all parallelograms. And the absolute value of the determinant equals the volume of that box. One important note, the determinant itself can be negative, but volume cannot be negative. The sign of the determinant encodes orientation. Whether the edges form a right-handed or left-handed system, the absolute value gives the actual volume. Here's the beautiful part. We don't need a brute force proof. We just show that volume satisfies the same 3 defining properties as the determinant. Property 1, normalization. The identity matrix has the standard unit vectors as its rows. Those vectors form the unit cube. The unit cube has volume 1. And the determinant of the identity matrix is also 1. Check. Property 2, row exchange. Swapping 2 rows swaps 2 edges of the box. The box doesn't change, the same shape, same volume. The determinant flips sign under a row swap, but the absolute value stays the same. Check. Property 3, linearity in each row. Multiply one row by a scalar t. The box stretches along the edge by a factor of t volume scales by the absolute value of t, and the determinant scales by t. They match. Check. For a concrete example, take the diagonal matrix with entries 2, 3, and 5. The box is a rectangular block aligned with the coordinate axis with side lengths 2, 3, and 5. Volume equals 2 times 3 times 5, which is 30. The determinant of that diagonal matrix is also 2 times 3 times 5, which equals 30. Every property checks out perfectly. Here is the logical capstone of our argument. We proved earlier that exactly one function satisfies all 3 properties. Let's list them. Property 1, f of the identity matrix equals 1. Property 2, swapping 2 rows flips the sign. Property 3, the function is linear in each row. Now, the determinant satisfies all 3 of these properties. Check. And signed volume also satisfies all 3 of these properties. Check. Here is the key insight. Since the uniqueness theorem guarantees that only one such function can exist, and both the determinant and signed volume satisfy the same 3 properties, they must be the same function. The determinant of A equals the signed volume. Therefore, the absolute value of the determinant of A equals the volume of the parallelepiped formed by the row vectors. And this is the deep reason why determinants measure volume. Now that we know the determinant equals volume, let's cash in on that insight. Back to 2 dimensions. Consider a parallelogram with one vertex at the origin and edges along 2 vectors, A, B, and C, D. We form a matrix with first row A, B, and second row C, D. the area of the parallelogram equals the absolute value of A times D minus B times C. Remember that parallelogram from the start? Its edges were the vectors 3, 1, and 1, 4. Let's plug in. A equals 3, B equals 1, C equals 1, D equals 4. The area equals the absolute value of 3 times 4 minus 1 times 1. That's the absolute value of 12 minus 1, which equals the absolute value of 11, which is simply 11. You can count the grid squares inside that parallelogram, roughly 11 square units, right? It checks out perfectly. Now here's a bonus insight. A triangle is exactly half a parallelogram. Two identical triangles tile every parallelogram. Just draw a diagonal. So a triangle with one vertex at the origin and edges going to the points A, B, and C, D has area equal to 1/2 times the absolute value of A times D minus B times C. Here's a satisfying confirmation. An orthogonal matrix, that's a square matrix whose rows are perpendicular unit vectors, produces a rotated version of the unit cube. Same shape, just tilted. The volume remains 1. Let's see the algebra confirm it. By definition, Q transpose times Q equals the identity matrix. Now take determinants of both sides. The determinant of Q transpose times the determinant of Q equals 1. But we know the determinant of the transpose equals the determinant itself. So determinant of Q times determinant of Q equals 1. In other words, the determinant of Q squared equals 1. That means the determinant of Q is plus or minus 1. Taking the absolute value, it's 1. Volume is preserved. A determinant of plus 1 means the rotation keeps the right-hand orientation. A determinant of minus 1 means it flips to left-handed, and that's a reflection. What about a triangle with no vertex at the origin? Take the vertices 1, 2, 4, 6, and 5, 1. We use a 3x3 determinant where each vertex becomes a row with a column of 1s appended. The area formula is area equals 1/2 times the absolute value of the determinant of the matrix with rows x1, y1, 1, x2, y2, 1, x3, y3, 1. Plugging in our vertices, the matrix is row 1, 1, 2, 1. Row 2, 4, 6, 1. Row 3, 5, 1, 1. Now subtract rows 3 from rows 1 and 2 to translate the third vertex to the origin. Row 1 becomes 1 minus 5, 2 minus 1, 1 minus 1, which is negative 4, 1, 0. Row 2 becomes 4 minus 5, 6 minus 1, 1 minus 1, which is negative 1, 5, 0. Row 3 stays as 5, 1, 1. Now expand along column 3. Only the bottom entry in that column is non-zero. The cofactor sign for position 3, 3 is positive, so the determinant reduces to 1 times the 2 by 2 determinant of negative 4, 1. Negative 1, 5. That equals negative 4 times 5 minus 1 times negative 1, which is negative 20 plus 1 equals negative 19. Finally, the triangle's area is 1/2 times the absolute value of negative 19, which gives us 19 over 2, or 9.5 square units. Let's step back and see what this really means geometrically. The determinant measures how a linear transformation scales space. Start with a unit square, which has area 1. Now apply the transformation defined by matrix A. The unit square deforms into a parallelogram, and the area of that parallelogram equals the absolute value of the determinant of A. So if the determinant is 2, the transformation doubles all areas. If it's 1/2, it halves them. Now here's the critical case. What happens when the determinant equals 0? The transformation collapses space. The parallelogram flattens down to a line or even a single point. The area goes to 0. The matrix is singular and its row vectors are linearly dependent. This connects the geometric story directly to the algebraic test for invertibility. Let's summarize the 3 cases. When the determinant of A is positive, the transformation preserves orientation and scales area by the determinant. And when the determinant of A is negative, the transformation flips orientation and scales area by the absolute value of the determinant. And when the determinant of A equals 0, the transformation collapses a dimension and the matrix is not invertible. A matrix is invertible precisely when its determinant is non-zero, precisely when its rows span full dimensional space. The same idea extends beautifully to any dimension. In n dimensions, the absolute value of the determinant gives the n-dimensional hypervolume. Here's the practical payoff. To compute areas from coordinates, you need no square roots, no angles, no perpendicular heights, just coordinates and arithmetic. This is why determinants appear throughout mathematics and physics. Let's summarize the key idea. The absolute value of the determinant of A equals the volume of the parallelepiped formed by the row vectors. There are three major applications worth remembering. First, coordinate geometry. You can compute area and the volume using only coordinates with no square roots needed. Second, Jacobian determinants. When you perform a change of variables in integrals, the Jacobian determinant tracks how the transformation scales volume. Third, cross products. The magnitude of V cross W equals the absolute value of a 2x2 determinant block. Whenever area or volume transforms under a mapping, the determinant measures the scaling factor. Now remember that parallelogram from the very start. With vectors 3, 1 and 1, 4, we compute 3 times 4 minus 1 times 1, which equals 12 minus 1, which equals 11. Now you know why that works. The determinant is geometry in disguise. It tells you how much space your vectors span.